Welcome to Advanced Programming with Java at Portland State University. In this lecture, we'll learn about how to develop automated tests using the JUnit framework. We'll also explore testing techniques such as unit testing and test-driven development. And finally, we'll discuss the Hamcrest API for expressing assertion conditions and tests more fluently. Software testing stands out as one of the most, if not the most, important tasks when you're doing software engineering. When your software is well tested, it's easier to document, it's easier to understand, and easier to extend. For many years, the JUnit framework has provided Java developers with a flexible and easy-to-use set of tools for developing tests for Java programs. We're going to talk about several aspects of testing Java programs with JUnit. We're going to talk about why you should test your code. We'll talk about the JUnit framework, its APIs, how to use it. Then we'll also dive into some advanced assertions with the Hamcrest library. Now, everybody knows that they should test their code. We all want our code to work, and we want tests to be able to verify that. But why don't we? Well, oftentimes we say, well, there's just not enough time. I need to write all the code. I need to get everything working, and yeah, I'll test it later, or maybe it'll be somebody else's responsibility. However, the less you test your code, the less confidence you'll have that it does what you expect it to do. Put it another way, ask yourself, how do you know your code really works, and works in the same way it did 2 minutes, 2 hours, 2 days, or 2 years ago? So I'm going to encourage you to break the vicious cycle of untested code. Don't wait until you think all of your code is done and perfect before you write your tests. I encourage you to write your test as you code, and ideally write your test before you start coding. And as you build your software, every new piece of functionality should have a test. These are called unit tests. So when you add a new method to a class, write a test for it to make sure that it actually does what you think it does. And then as you're developing more and more code, run your tests every time you recompile, to make sure that your new changes haven't broken anything that used to work. Back in the mid-90s, people like Kent Beck began evangelizing the concept of extreme programming. It sounds like something out of the 90s. Extreme programming acknowledged that software needs to be developed quickly and needs to evolve even faster. Ideally, if you can keep up with the customer's demands, you'll win in the market. Extreme programming also popularized the notion that software engineers should work together. Pair programming was first introduced as part of the XP movement and has taken on new life now as mob programming. XP calls for writing tests along with the code being tested, and so you develop your tests at the same time that you write your code. It also acknowledges that it takes many roles to write software. In addition to people writing the code, you need architects to think about the bigger picture, and you need a manager to make sure that the problems are well understood and well executed. And of course, you need the customer. The customer is the person that is asking you to do something, that ultimately wants some value out of your software. And providing frequent and constant feedback to the customer, it ensures that the customer gets what they want. Another tenet of extreme programming is that the software must function and function correctly at all times. So even if you're starting out really small with just a little piece of functionality, you need to make sure that that functionality works as expected, and then as you build on it, as you add more features, as you evolve your software, you want to make sure that things still function as expected. And by working incrementally in these small batches, XP emphasizes simplicity and elegance in software engineering. So the whole idea is that the first thing you do is get things working, and prove that they keep working as you optimize, as you improve, and as you add new functionality. Now these principles and tenets of extreme programming work very well when developing object-oriented software. When you think about the increments that you build in OO software, you have classes that are extended to add new functionality. You're adding new methods, maybe you're changing existing methods to have things do more things. And when you add that new functionality, add new tests to make sure that the new functionality behaves as expected. And then to make sure that the things that you did before still work, you have the old tests, the existing tests that verify the expected behavior. So just like documenting your code as you go, testing your code has many benefits. Continually running tests gives you confidence that your code still works. Automated tests help you find bugs in your code before someone else does. And you become a consumer of your own code. You'll be able to tell yourself whether or not your code is easy to use, especially if you come back to the code after a couple of days. Did you choose good names for your methods and fields? Are your algorithms easily expressed inside the code? And finally, if you run your tests every time you do a build, you know that your changes haven't broken anything. What this allows you to do is move forward confidently and quickly because you've got a sanity check every time you make a change. The test-driven development approach, or TDD, advocates for writing tests before the code being tested is written. So you write your tests first, then you make them pass. TDD helps focus on the immediate problem to be solved before the solution is implemented. By writing a test first, you understand what your code needs to do before you write the how of what it does. This approach helps reduce wasted code that isn't absolutely necessary and emphasizes simplicity in your code. It applies the Yagni principle. You ain't going to need it. So the whole idea is that if you write the test first and then just do the minimal amount of work necessary to make that test pass, well, clearly all of your code is necessary. You're not adding extra functionality that ultimately won't be used. And by working in small chunks, it allows you to get rapid feedback on your work, and again, helps you go faster because you have confidence. Test-driven development occurs in 3 phases. The first phase is called red, meaning that you have failing tests. You write a test that compiles, so it can be run, but it fails because the code that it tests hasn't been implemented yet. After the red phase is the green phase. This is the phase of test-driven development where you write the code that make the test pass. And that's all the code that you write. You don't write any more than that is necessary to make the test pass. So now you have the behavior that you want. The code is working. But the final phase in test-driven development is the refactor phase. And this is where you take a look at the code that you've written and ask yourself, can it be improved in some way? So for instance, can I make the code more efficient? Can I make it easier to read by improving the names of things, such as methods and fields and variables? Can I eliminate duplicate code? Can I take similar code that appears in 2 places and replace it with one set of code that's called twice? And after you've made those improvements, you run your tests again to make sure that they still pass. As your application grows in size and as your code base is developed, you'll want to consider different types of automated tests for all of the behavior in your application. In fact, there are 2 types of scopes that you'll want to consider. The first scope of automated tests are called unit tests. These are small tests that exercise the behavior of a particular unit of code, so a particular class or a particular method. These unit tests are meant to run very quickly, on the order of milliseconds, only do a couple of things, and require very few dependencies, so you're really having very targeted tests in isolation. And because they provide such rapid feedback, they're meant to be run every time the code changes. So you add a little bit of code, you run your unit tests, and you verify that nothing's been broken. So unit tests are great for simple, localized behavior. But for more complex, global behavior, there are integration tests that exercise the behavior that requires multiple modules of code, multiple classes working together, and maybe even multiple systems that are working together. So for instance, integration tests often require some sort of environmental setup. So starting a database or spinning up a web server. These tests take on the order of seconds or even minutes to run if they do very complex things that require lots of moving parts. So integration tests are meant to be run less often, but ought to be run before code is shared with others. That is, before you check it into version control. So as you're developing, run your unit tests after every change to make sure the functionality is still correct at the unit level. And then periodically, and certainly before you commit your code, run your integration test suite. And this will give you broader feedback on the larger functionality of your application. Now, regardless of whether they're unit tests or integration tests, these automated tests can be executed from an IDE, from a build system using something like Maven or Gradle, or your continuous integration processes. And again, tests are all about feedback. Because they're integrated into the tools that you use or are either invoked automatically as part of a build pipeline, you'll get that feedback from the automated tests. Over its long lifetime, the JUnit framework, initially developed by Kent Beck and Eric Gama, who also was one of the Design Patterns Gang of 4 folks, has become the pretty much de facto standard for unit testing in Java programs. And you can also use it to do integration testing to a large extent. I encourage you all to visit the JUnit website, www.junit.org, to learn more about the framework and its history. In this lecture, I'm going to cover a little bit of the history, but I'm going to focus mostly on the most recent version of JUnit, JUnit 5. However, I want to make sure that you have a good feeling for how JUnit has evolved over the years, because outside of the class, you may very likely encounter JUnit tests that are written using some of the older APIs. I want you to have a conceptual knowledge of how those older tests were written. So initially, there was a Java package called JUnit.framework that contained a simple class hierarchy for writing unit tests. At the top of the class hierarchy was a class called assert. And assert contained a number of static methods that make assertions about a certain program state. So when you write a unit test, or really any test, you establish some condition, you perform some operation, and then you assert that what you expected to happen actually took place. I like to refer to this as the given, when, then portions of a test. And so when it comes to asserting that things have taken place or checking that what you expected actually occurred, you can use the methods in the assert class, and we'll dive into them in a little bit. Now, in the initial JUnit framework, there was also a class called testCase, which extended assert. This is the actual test that was run. And your code would then subclass testCase, invoke its constructor with a certain name. You could inherit and override methods like setup and teardown to do any setup code that needed to happen before your test is run, and then to clean up afterwards. So let's say you wrote some data to a file in the setup, your test then exercised the information in that file, your teardown method would then delete the file. The initial JUnit API also had the notion of a test suite, which aggregates together multiple test cases. And so, for instance, a test suite would consist of all of the tests in a certain Java package, or hey, maybe all of the tests related to a specific piece of functionality. In early JUnit, there was a very important coding convention. So when you want to write a test of your own, you would subclass test case. The way the JUnit framework that runs the test would know that a particular method represents a test case is that its signature would have a public scope, would have a return type of void, and it would have a name that began with all lowercase test. So this was a pattern that you had to follow, a convention that you had to follow when you wrote tests in early JUnit. This initial version of JUnit was incredibly successful. It really opened a lot of people's eyes, including myself, to how easy it could be to unit test your code and the confidence that it gave you. However, there were still some things in the framework that were kind of awkward. Because you were required to subclass test case, it meant that your tests couldn't subclass anything else. Usually you get around it by having a class hierarchy of tests, but it was a little awkward that everything ultimately had to extend from JUnit. And the naming convention, while it was easy for humans to understand, sometimes tools struggled to locate exactly what methods were test methods. And of course, if you misspelled the word test, if you accidentally had a capital T or something like that, the tool wouldn't be able to find it. So in version 4 of JUnit, they introduced Java annotations in the org.junit package that are used to denote your test code. So if you have a method, regardless of its name, that is annotated with the @test annotation, this indicates that it's a test method. Now the test annotation had a couple of attributes. One of them was called expected, which allowed you to give the class of an exception that was thrown by the method, meaning that you expected the test to throw an exception, which is a completely valid thing to do, and we'll talk about that in a moment. And you could also specify a timeout for the test in milliseconds. Again, maybe you've got some operation which is known to take a long time, or maybe hangs or something like that. By specifying a timeout, you can make sure that your test will continue even if this particular test took much longer than expected. A couple of other annotations that you may run into when working with JUnit 4 code. The before annotation, @before, is used for setup methods. This allowed you to have multiple setup methods in a class. And similarly, there was an @after annotation for tearing down the scaffolding for your unit test. Now, @before and @after were run before and after every test was invoked. But you could also use the @before class and @after annotations for setup and teardown methods that are invoked before all of the tests are run. Now, sometimes you'll write a test, and maybe it's not meant to pass yet, or maybe it used to pass and now it fails, and you just don't want to worry about it anymore. Instead of deleting the code for that test, JUnit allowed you to place an @ignore annotation before that method, which indicates to the JUnit framework that yes, it's still a test method, but it's not meant to be run anymore. And then when the JUnit framework runs your code, it can note that in the output. So you'll often see when you run JUnit tests, you'll see here's how many tests passed, here's how many tests failed, and here's how many were ignored. JUnit 4, because it was introduced along with Java 5, I think that was the version, that allowed all these new language features like annotations. You can also have a static import for the assert methods, which was nice. It made your assertion statements a little less verbose, because now you didn't have to type the word assert anymore to invoke static methods like assert true and assert equals. JUnit 5 continued to mature testing support for Java programs by providing a new programming model called Jupyter. It also continued to acknowledge the importance of having robust frameworks for running JUnit tests by providing a platform that can be used by a bevy of tools, and then also contains backwards compatibility support for older JUnit tests, because there's still a lot of those out there in the field. So the Jupyter API, which we'll be exploring in the next couple of slides, leverages Java 8 language features so you can have richer tests, and also just fixes a couple of things that have been awkward in JUnit over the years. And that's what you interact most with JUnit 5. But it's also important to understand that JUnit 5 also includes something called the JUnit platform, which makes the interaction with tools like IDEs that launch test frameworks very explicit. And then again, it contains a bunch of modules and APIs and tools for making sure that your JUnit 3 and JUnit 4 tests still do what you expect them to, even though they're running on a completely new engine. Now we're going to explore the JUnit API. And in order to do that, we'll be writing some unit tests that exercise the behavior of a simple application that models students that are enrolled in a section of a course. And so this is the code that is under test. We have a course class that is in a department. Each course has a number and a number of credits. And a course is associated with 0 or more sections. Each section has a term and a year, both represented as integers. And it also has a bunch of methods, a bunch of behavior. So you can add a student to a section, you can drop a student from a section, you can compute the average grade and get the size of the class. And then sections and students have a many-to-many relationship, and each student has an ID and a map of grades that they have in their classes. So this is the domain that we're modeling, and now we're going to look at some unit tests for that. Although I do want to note that in test-driven development, we would probably have this sketch first, but we would write unit tests first and then go write the classes. We're not going to see that in these slides, but that is the approach that I would recommend taking when developing code that is well tested. So here is a test class that validates that when you add a student to a section of a course, the overall enrollment count is increased by 1. This is a good example of a unit test, right? It does something very simple, but it's something that's important and fundamental to the behavior of your program. So note that test code exists in a class that is separate from the code being tested. In this case, I have a class called section tests that tests the section class and its behavior. So this is plain old Java code, just like any other piece of code. So it has a package declaration. It lives in some package. Here again, it's the example JUnit package. And then in order to use classes from the JUnit API, it has some imports. So the first thing it imports is the org JUnit Jupyter API test annotation. So that is an annotation that the test class is going to use. And it does a static import of a couple of methods from the assertion class. The assertions class is what contains the assert equals and assert throws methods in JUnit 5. And note that in order to fit the entire class name on the slide, I have a couple of dashes. The fully qualified name of the assertions class is org.junit.jupyter.api, capital A assertions.assert equals. But I wanted to make sure it fit on the slide. The real interesting part of the test is what happens in this test add student method. So that method is annotated with @test, meaning that it is a test method in JUnit. So a JUnit runner will identify this as a test that needs to be run. And then what does the test do? Well, the first thing it needs to do is set up some context in which the test is run. So in this case, I create a student object, I create a course object, and I create a section object. That is that given part in the given when then format of a test. So I've set up that data. Now I'm going to perform some operation. This is the when part. So I'm going to add this student to the section by calling section.addStudent. And now I want to make sure that the behavior that I expected actually took place. And that's where I will use the assert equals method that I've imported from the JUnit API. So I will say, okay, I'm going to assert so that I expect that there is one student in the section. So the assert equals method takes 2 parameters. The first one is the expected value of something that you expect to be equal, and then the second one is the actual value. So here I expect that 1 is the value returned by getClassSize. If when this test is run, the class size is not 1, the assert equals method will fail. It'll throw an exception that is caught by the JUnit framework, and the JUnit framework that runs the test will then keep track of the fact that this particular test failed. That was our first JUnit test. Let's take a little detour and explore the assertions class a little bit more, and then we'll take another look at a unit test in a moment. So the assertions class contains methods that validate that certain conditions are true. Again, this is that when part of your given when then test. Assertions contains a method called assert equals. You've got two values and you expect them to be equal. Assert equals is overwritten to take any kind of object, int, all the primitive types, double, long, all that kind of stuff. And it compares an expected value to an actual value. And note that when you compare object types, the dot equals method is used to compare them. Assertions also has a method called assert not null, which asserts that, some value that you have calculated by running your test has a value that's not null. Assert same takes two object references and asserts that they should be the same. They are compared using equals equals as opposed to dot equals, which is what's used in the assert equals method. If you want to make an assertion about a Boolean expression, then you can use the assert true method from assertions. And finally, assertions has a method called fail, which just fails a test outright. Maybe you perform some other comparison operation to an expected value and an actual value, and you've determined that your test has failed, that the condition has been met. And you can just fail it outright by using the fail method. So anytime one of these assertion methods evaluates to false, the test fails. And again, the framework that runs the JUnit tests will keep track of this and note it appropriately. Now, when an assertion fails, it's very helpful to understand what was being asserted, what exactly was being compared. Because otherwise, you get an assertion error saying like expected 3 but was 4. That doesn't give you a lot of context. So every assert method is overloaded to have a string message that's associated with it. So there are two argument versions, like assert equals of 1 and section.getClass. And if you want, you can then add a message that is displayed with the assertion failure that gives a little bit more context. So in this case, you could say wrong number of students. In my experience, this is very helpful, but it's not something you want to do every time. So what I find myself doing is that I'll add this context only after the test has been passing for a long time and then suddenly fails. In the one example we saw a couple of slides ago, that was a happy path. We expected that that the behavior will be as expected, and that the data that we set up and the operation that we perform will have the outcome that we want. But it's also very important to make sure that your program, that the APIs that you write, the code that you write, fail and convey errors in a well-understood way. Remember, like we talked about before, the exceptions are part of a method signature in Java. And so when you write tests, you want to assert that not only does your method perform the operations that are expected on a given set of inputs, so the return value is what you expect, but also when bad data is given or when the object gets into a bad state, the appropriate exception is thrown. And so here is an example of how you can validate that the drop student method throws an illegal argument exception when you attempt to drop a student that isn't enrolled. So here is another test method inside that same section test. The name of the method is test drop student not enrolled. And here we set up some data. So we're going to create a new student, we create a new course, and we create a new section. And now we want to say, well, hey, when drop student is called on that section, and remember the student wasn't registered in that section, we should expect an illegal argument exception to be thrown. And the way you express this in JUnit 5 is you use the assert throws method. The first argument to the assert throws method is the class of the exception that you expect to be thrown. In this case, it's illegal argument exception.class. And then the second argument is an instance of an interface called executable, which is part of the JUnit API. And executable has a single method that has a return type of void. It's called execute, doesn't take any parameters. And this makes an excellent fit for Lambda expressions. So you'll see we have a Lambda expression there of paren, so there aren't any arguments to that Lambda expression. And what does it do? It calls section.dropStudent. So that is the when in your test. That is the behavior that you're executing. Now I realize that this lecture happens pretty early on in the course, and we haven't talked about things like what illegal argument exception.class means exactly, and we certainly haven't talked about Lambda expressions yet. It's okay, just get used to this syntax for now, or feel free to skip ahead to a couple more lectures to learn about Java reflection and doing functional programming in Java. But the bottom line here is that the assert throws method allows you to validate that when something goes wrong with your code or when an error is detected by your code, the error is indeed corrected and expressed in the correct way. And this is important, just as important as making sure that the happy path through your code is as you expected. Now note that maybe some other exception occurs. And in that case, what will happen is that the exception won't be caught by your test itself, and instead will bubble out of the test method. And in that case, the JUnit framework will catch it, will log it, and it will mark the test as errored. So there's a difference between a test that fails and a test that errors out. So a test that fails has a condition which is not met, so it makes an assertion, and that assertion proves to be false, as opposed to a test method which is in error, which is one in which the test method is run but encounters an uncaught exception or an unhandled exception, and then is noted as so. Both of these are not what is expected, but they mean different things. So to emphasize, your test class is just regular Java code, right? You have a class, it's got methods, you put annotations on it, it calls APIs, right? Really there's nothing special here. It's just what its job isn't to model data and perform operations in your application. It's instead, its purpose is to validate that your application, that the main code, the code under test, behaves as expected. So there's some other things that you should know about when it comes to writing test code. If you have setup and teardown methods, you can annotate those with at before each and at before after. And the JUnit framework will invoke the before each method, before each test method is run. And of course, after each is afterwards. And this allows you to do things like create test data that is used by multiple tests. You can store that data inside a field of the test class, the object that's created to represent the test. And these are new names of the at before and at after annotations that we talked about in JUnit 4. Each of your test methods must be annotated with @test. That is the direction to the test framework that lets it know that these are the methods that ought to be run. When you have a test class or a test method, they can have default scope, meaning they don't have a public or private or anything. This is basically package level protection. They can be in default scope in JUnit 5. In JUnit 3 and JUnit 4, they had to be public. This doesn't seem like a big deal, but it's kind of nice just to be able to remove that word public from all of your class and method declarations. And finally, JUnit 5 allows you to use inner classes, which again, we haven't seen it, but you will in the reflection lecture. JUnit 5 allows you to have inner classes that allows for nested tests. And depending on what exactly your test scenario is, this can lead to very fluent display names and a really quite elegant way to express kind of complex combinations of testing scenarios. I really encourage you to read up on all the stuff that's there in JUnit 5. It's a really nice evolution of JUnit, but I think the criticism that JUnit has gone very far from its initial origins is a very simple API. It is more complex now. It has a lot more features, but they're good features, and it's things that have been developed and evolved over a number of years. I think it's probably fair to say millions of unit tests that exist out in the world. Now, to dig a little deeper into the Jupyter API, there are a lot more annotations out there that allow you to configure your tests in really interesting ways. I won't go into examples of all of these, but I did want to highlight some of them here just for your general knowledge, and maybe it'll give you an idea of something that you can use in your own unit tests. In JUnit 5, in the Jupyter API, @ignored has been replaced with @disabled. And @disabled instructs that the test runner not run the test or the test class. You can also annotate an entire class with @disabled. You can also specify the display name of a particular test. And this allows the reporting tool to display it in a way that's maybe a little bit more human readable than the name of the test itself, or the code, the name of the test method in the code. In JUnit 5, you can use a timeout annotation to specify the amount of time that the test should run before the framework times it out. And there's also a little bit of a dependency injection in JUnit 5. We'll explore that that concept in a later lecture. But let's say, hey, you've got a unit test and you want to create a file in a temp directory. Instead of having to have your test figure out exactly where the temp directory lives and worry about cleaning it up and everything, the JUnit framework can take care of that for you. And so what you can do is you can have a parameter to your test method or a field in your class which is annotated with the @tempter annotation. And when that test is run, the value of that field or the value of that parameter will be populated with a Java IO file object that contains temporary files. It's very common to have a test that is parameterized, meaning that the behavior of the test is the same. It performs the same operations, but you want to do it with a variety of different data. So let's say you're validating something like a phone number, and you want to test your validation with various types of inputs. So maybe a valid phone number or a bunch of invalid phone numbers is probably more likely. Ones that maybe don't contain enough digits or contain letters in addition to numbers or emojis or whatever. Writing a separate test class or a separate test case, test method for each of those is onerous, can be hard to read. And so then in JUnit 5, there is a @parameterized test annotation that allows you to specify that this test ought to be run multiple times with different parameters. And you can go read about it in the API documentation, but there are a variety of sources that the parameters can come from. You can give it an array, you can give it a method that populates the data, comma-separated values, all sorts of good stuff. It makes for very readable and concise automated tests. Now, you have a test class, and in the test class are declared multiple methods. Ideally, the order in which the test methods are invoked shouldn't matter. Each test method should be idempotent. It should be able to be run in isolation from everything else, right? And so it should have its own setup, its own teardown. It shouldn't leave anything around that future tests depend on. However, this isn't practical in every situation, and sometimes what you want to do is specify, hey, I want my test methods to be run in a certain order every time. To do that with the JUnit API, you use the @test method order annotation. And here you can specify that you want the tests to be run lexicographically, alphabetically, by their name, by their display name. You can also provide an @order annotation for each method. You can also say it's random each time. Probably not what you want to do, but maybe it's good to sort of experiment with that. And finally, there is an @tag annotation, which allows you to categorize tests into certain subsets. And this is most helpful when you have a large suite of tests, and in any given scenario, maybe you don't want to run all of them. So maybe you've identified that some of your tests are what are called smoke tests. These are the sanity checks, like, hey, run this suite of tests to make sure I haven't broken anything fundamental. Or maybe there are certain of your tests that are performance tests that take a long time to run, or really only should be run in certain environments on certain pieces of hardware in certain conditions. These tags allow you to classify tests together and only run tests that are tagged in a certain way in a particular scenario. Now, I mentioned that test classes often mirror the class that is under test, right? We had section test and we had section. They were in the same package. But is this really the right way to go? Well, there's some pros and cons. The nice thing about having test code and the code under test in the same package is that, hey, if you've got some piece of behavior, a method or a field that you want the test to be able to access, you can just give it default visibility. That will allow classes in the same package, so a test class in the same package, to be able to reference that field or that method that has package level visibility. Well, that's nice. It's also easier to associate the test code with domain code because they're there in the same package. You're sort of looking at them side by side. However, when it comes to your tests, you want to make sure that the test code doesn't interfere with the domain code. You want to make sure there's a very clear separation between the two. And you certainly don't want to ship your test code, right? This is not code that the end user runs. This is not code that is run as part of a production deployment. This is code that is meant to be separate. And so you need to balance providing the access that the test needs to the code under test, to the main code, while keeping them separate enough so that just the main code is deployed and can run independently of the tests. Over the years, and for a long time now, it's become standard to have a separate directory hierarchy for the test code. When we learned about the Maven conventions, they have the test code in source test Java, and then you have your package name, just like you have source main Java for your main application code, the code that is under test. And this has worked out really well, and this is the way everything works now. So JUnit is great. It works really well, and it has all those assertions, which let you do a lot of stuff. But the code and the failure messages can be hard to read sometimes. When you're writing a test and you've got a test that fails, especially when you expect it to pass, you want to have a clear, concise error message that then helps you on your quest to debug that failure and get things working again. So consider the following statement. Let's say you perform some operation and you want to validate that the string returned by that operation contains the string hello. Well, using the JUnit assertion APIs, here's what you need to do. You need to say, well, assert true, my string, which is the string that was returned by the code that was under test, contains hello. And when this passes, this is fine. The test passes, is great. But when it fails, let's say that my string doesn't contain hello, what happens? The expression myString.contains hello is evaluated. It returns false. Then what JUnit says, okay, assert true, false. Oh, that's a failure. But all it knows, what all JUnit knows, is that you expected true and got false. It doesn't really tell you what went wrong. And then you sort of need to start the chase to figure out, okay, well, hey, why did this assert true fail? Oh, it was because this condition wasn't true. Then you got to run the debugger and everything. There is a library called Hamcrest, and Hamcrest is an anagram for matchers, which provides, well, what they call these matcher objects that provide much more readable assertion statements in the code. And then if something fails, if the assertion fails, they provide a much more detailed and specific failure message, which allows you to start your debugging journey even quicker. I'm going to cover some of the highlights of the API, but I encourage you to check out hamcrest.org/javahamcrest for all of the details about how these classes work and the wide variety of assertion statements that are available to you. So Hamcrest provides a method called assertThat. This is a static method that's imported, that makes some assertion that a value matches an object called a matcher. And so each of these matchers have what's called a static factory method, so you can create them just by calling one of these methods. For more complex assertions, you can compose these matchers together to say, okay, yes, I want to assert this fact and that fact, or I want to, well, we'll see lots of examples. There's also a matcher called is, which really doesn't do much of anything, but it's nice syntactic sugar that lets you read the assertion statements a little bit more easily. So I'm going to walk through some examples of how to use this Hamcrest API and some very simple unit tests. But I'm sure you can imagine how this would be applied to more complex situations, maybe even the tests that you write as part of your assignments. So just like with any Java code, you have a class that's in a package, and you need to import some APIs in order to use them. This unit test uses the JUnit test annotation to indicate that, yes, this is a method that is a test. But then it also uses some APIs from the Hamcrest library. It'll import all of the methods from the matchers class, and then the assertThat method from matcherAssert. And this allows you to write unit tests like the following. So the first one is equal to. And what this one does is it uses the Hamcrest API to assert that one integer object is equal to another one. And the way you write it is much more fluent, right? This reads much more naturally. So you say that assertThat int1, comma, is equal to int2. And so the assertThat method allows you to say, hey, I expected a value of int1, but what I really got was int2. Is that okay? Is that equal? Here's some other examples of using the Hamcrest API. There's a matcher called null value that you can use to say, hey, assert that some value, null in this case, is null. There's same instance, which asserts that two objects are the same using equals equals. And here's where Hamcrest really shines. Here are some examples of the string matchers. So you don't have this kind of stuff out of the box with JUnit. This is why I like to use Hamcrest for these kind of matchers. So let's say I've got some string, like Hamcrest is awesome. Well, I can make a number of assertions about that string. I can assert that it starts with a certain value and it ends with a certain value. And that contains a certain string. You can do this with plain old Java APIs with a string API and the JUnit class, but it doesn't read as easily, and you certainly don't get a nice error message. So let's say that the string s doesn't start with Hamcrest. The error message will actually say, I expected that the string started with Hamcrest, and in fact it didn't. Much more fluent, much more easier to get started debugging it. You can also make assertions about is the string empty, and also assertions about whether or not it equals a certain value, ignoring case. And again, these are all APIs that come from the Hamcrest library, but it mirrors the kind of stuff that you would have in the plain old Java API. Hamcrest also has really great support for working with collections. So let's say I've got a list that contains A, B, and C. I can do things like, hey, assert that every item in that list has a non-null value. Sure, you could do this yourself, but you have to write your own code to iterate over the list, or maybe use something from the Stream API. This just does it for you. This is a nice advantage of Hamcrest. Similarly, I can make assertions about numbers. I can say, hey, is one number greater than or less than another? I can use the both matcher to specify, hey, is this number in a certain range? And I can also use the close to provide a tolerance to say, hey, I want to make sure that it's within a 0.01 of a certain double value, right? And so then, as you're doing numeric stuff in your programs, this can be very helpful. And just like we did with the example of collections in the first method here on the page, we can make assertions about arrays. So you can say, hey, does an array contain a certain item? Does it have a certain size? Is it empty? Is a particular value in the array? All very helpful things that make your test code easier to read and your error messages more actionable. So in summary, testing might be new to a lot of you, especially writing your own tests or having automated tests, but believe me when I say this is a good thing. Testing improves the quality of your software because it lets you validate the quality of your software. It ensures that you can demonstrate to yourself and to anybody else who's looking that your software works as expected. So if you practice test-driven development and if you write your tests as you code, it's not a big deal. It's not something that you do after the fact. It's something that you do as you're writing the code under test. And this will give you rapid feedback to make sure that the stuff that you're writing new works as expected and the stuff that you did before still works. Overall, I've found that the time that you invest writing tests reduces your debugging time extensively. And as your problems get more and more complex, debugging takes longer and longer. So by working in small batches and small increments along the way and having a unit test for each one of those, you find out that you just stop debugging. Right? There's no need to debug because when something goes wrong, you detect it immediately. And you can very easily figure out, oh, right, I just made that change over here. Wow, that broke that thing over there. Okay, well, now I know where to look for the failure. So instead of diving into code in debugger, I dive into code in unit tests. The JUnit framework and the Hamcrest API make it really easy to write and run unit tests. These two libraries have been vetted by hundreds of thousands of Java developers all over the world. They work really well. They're really effective for expressing things, and it allows you to really jump into test authoring really easily and helps you be successful. And of course, by testing your code to making sure that you have validated the requirements of the assignments and anything else, it'll help you get an A in this course.